Thanks for waiting. We'll get started. Our last speaker for this session is Mike Graham, and he'll be talking about the life cycle of a Python class. Please welcome him.
Thank you. So the idea of this talk is that we are going to write a really simple class, about as simple as you can, use it in a really basic way, and then see sort of everything that happened along the way, which actually adds up to a whole lot in a language like Python. My number one pet peeve about like a big talk at a tech conference is trying to put code up on the slides because no one's going to be able to read it. And so to ameliorate that a little bit, if you want to follow along on your own device, bit.ly/PyCon slides will contain the slides we'll be going over. I try to make all the code as big as possible. There's not too much of it, but in case you did want to follow along. So we're going to go through mostly focusing on descriptors and metaclasses. I hope you didn't actually want to learn how to use those things. If you did that, you should have went to the half-day session Mike Mueller gave during the tutorials. But we're going to see when those mechanisms are triggered and see, sorry, my screensaver. So we're going to, like I say, see when those are triggered and where hooks could have happened or did actually happen in the code that we're going to look at. So let's meet our class. It's sort of the most basic class I could think of. It's a really, really bad fraction class. So it starts with a class declaration and ends up having three methods. Under, and init, which just takes a numerator and a denominator, sort of what you'd expect. Under, mul, so this implements fraction multiplication, so it multiplies the numerator and the denominator and makes a new fraction out of it. And then a print fraction method that just prints out the numerator / the denominator. You'll notice that's a Python 2 print. You kind of have to make a choice, and we're going to use Python 2 primarily for this talk because there's more asterisks and provisos there. There's been some simplification in Python 3. So down at the bottom, we just have a simple interpreter session where we use it. We make the fraction a half. We multiply a half times a half and see that it gives us the result that we thought, quarter, 1/4. So looks like really simple code, but a lot actually went on here. So the first thing you'll notice, we inherited object, which is this thing that you're always supposed to do in Python 2 and really doesn't add much. There's no like methods of object that you want access to. The reason that we inherit object isn't actually to do with subclassing at all. It's to do with metaclass propagation. In Python 2, there were two completely independent object systems. Classic classes, which is how classes worked in early versions of Python, and new style classes, which is what we end up using when we inherit objects. So when you inherit, you use the metaclass of the thing that you're inheriting. And that's how we end up getting a benefit here, is that we're actually, this basic code that you do all the time, invoking this somewhat obscure feature, metaclasses. So let's go through and look how metaclasses work, what they do. So in a lot of ways, the scariest thing about metaclasses is the name. The API is also a little scary, but a lot of people are overly intimidated about them. So a metaclass is just the class of your class, the type of your type. So a class, just like everything else in Python, is just an object. So obviously, it's going to have a class. It's going to be an instance of a class. And that's what metaclasses are. Another parallel, only partially compatible thing about metaclasses is that they're just callables. So metaclass is what gets called when you write a class. So the class syntax, the class block, is just syntactic sugar for calling a metaclass. So metaclasses let you make things that are not classes using the class statement. So if you've used Django and made a model, Django model is not a class, even though it looked like a class when you made it. Or if you've used the standard library enum module, like I am here at the bottom, it looks like we just made a class that had the parent of enum. Then if we look, we ask what's the type of our class? It's an enum meta. It's not a type. So contrast this if we had inherited object, or in Python 3, if we had inherited nothing, we would have made a class, so its own class would be type. So this Boolean, enum Boolean class, what we inherited changed the type of what we got. It wasn't just true inheritance where we're getting parent methods and data and so forth. So just to look at some of the contrast here, if we look at an attribute, say the true attribute, in the Boolean enum, we get an instance of our Boolean enum itself, something very special as that .true. With our class on the right, we just got the one that we put in there. There's been no processing because that was just a normal class. We saw that the type of the class was different, or the type of the attributes are different because they've been processed. And if we try to make an instance, we see on the right, we could make an instance of our class fine. On the left, the Boolean enum works different. And at first glance, you might think, oh, it just had an init. If you read the traceback in detail, you see that it's not just that, it's that Boolean enum works fundamentally different. So you can specify metaclasses explicitly. We talked about inheriting and getting your parent class's metaclass, but that only works after you have an instance of that metaclass. So the API was given to us to use metaclasses directly. The main thing I can think of that actually asks you to do this is the standard lib ABC module. The inheritance way of going about it is much more common. But in Python 2, you just set as an attribute under metaclass to the metaclass you want to use, and that will make the class myABC not a class, but an instance of that metaclass. There's also an alternative syntax in Python 2 that wasn't very widely adopted. The idea was I want to change it for my whole module, and so you can actually set module level under metaclass, and all your classes will be instances of that metaclass. The idea at the time was, well, you set that to type, and you're using new style classes, no classic classes ever, and then someone remembered that it's not nice to have something far away from your code changing what your code does, but that is something that I've seen used in the wild and can really throw you for a loop. In Python 3, somewhat nicer syntax was given to us. It's like a keyword argument in a class definition to set a metaclass. So this is much less cumbersome, much nicer to use explicitly, but people haven't really started doing that a whole lot. And so we end up with a lot of these implicit via inheritance metaclasses. So let's go through and look from a couple angles at what metaclasses do to hopefully flesh out what happened. So let's define something we're going to use as a metaclass. We're just going to make a really, really useless metaclass here. It's called myMetaclass. Instead of giving you a class as a result or anything useful at all, it's just going to give us 7. And we'll see that when we use this metaclass, we'll just get 7. Realistically, metaclasses people would actually write, especially these days, now that we have class decorators, wouldn't be functions, they'd be types, they'd be richer things. This type of metaclass used to be more popular, that didn't make a new class at all, but just processed some data. So we see that metaclasses, like I said, they're just callables. They're what are called when you use the class statement. So they take 3 arguments. I call them here name, bases, and D. So we'll print those out and see what those are. So we define what looks like a class, but it's not really, called just7. We're going to inherit from a couple strings, and we're going to use our metaclass. So instead of making a class, we're going to hand everything from our class block to my metaclass. We're also going to put an attribute called foo in there so that we can trace it through. And so we get this print because we're using this metaclass. That means that this entire class block is just syntactic sugar for calling the function myMetaclass. And so what was it called with? The name. So the first thing was, I said class just7. That just7 right there comes in as a string. And then everything I inherited from, in this case 2 strings, come in as a tuple. And so we see that those come in. And then we get a dict of all the attributes that were in the body of the class. So under module was automatic. Python put that in for us. Under metaclass and foo were things that we put in. And we see that those come through. So everything from our class statement, rather than being made into a class on its own, were passed to the metaclass we specified. And so since we returned 7, just 7, instead of getting assigned to a class, got assigned to just 7. And so that's the level of flexibility that metaclasses have. They just allow the class block to be another way of calling a callable. So from a different direction, we're going to look at another example. We're going to remove the syntactic sugar and go through and make our fraction class without using a class statement. So we see that the metaclass of fraction, like I told you, was type. It's sort of the most basic metaclass in Python, the one that your normal classes should be. And so we're going to call type ourselves instead of having the class statement itself call type. First, we'll define all of our functions just as bare functions. All methods in Python start their lives as normal functions. That's why they just take self as an argument. There's no special thing at definition time that makes a method a method. Self could be called anything else. That's why you have to put it there. So we're just going to define them completely plain before we do anything. And remember, the attributes of our class, the assignments in our class block came through in a dict. So we'll just make that dict. We'll call it attributes. And that'll let us use our init as under init, our under mul as under mul, and so forth. And so we'll just call type ourself and do what the class statement would do before. With the name, we had called it fraction. The bases we had inherited from object, so that comes in as a tuple. And then the attributes that came in as a dict. And so that's sort of the other direction of what metaclasses provide. And so the big takeaway is that this is just another way of calling what Python allows to be a completely arbitrary function. Two other quick notes. There are a couple other things that can trigger in metaclasses. One is called under prepare, which allows you to use something other than a dict, sort of beyond the scope of this, but the killer app for that is having an ordered dict. So you get your attributes in the order you defined them, if someone was defining one of those. And it looks from discussion like 3.6 might have another method, under descriptor, that lets you not use that dict at all, or even your alternative to it. So one of the important things about metaclasses is that they're completely invisible. You can't tell that you're using them, where you're using them. You have to know from what you're inheriting from what it is. You have to ask yourself, is this really a class or is it something else? And a lot of things that apply to a class don't apply to an SQL alchemy model, don't apply to these other things that people use metaclasses for. The most common application we really use for specifying metaclasses is new style classes. If something weird is happening in Python 2, maybe you didn't inherit from object or something else that would give you that metaclass, and you're using classic classes that work differently in subtle ways. Now that we have class decorators and have for several versions, a whole lot of use cases that used to be primarily used for, primary uses of metaclasses are now easier and less invisible to express in terms of class decorators. So if you're ever tempted to use a metaclass and you don't know what a class decorator is, figure out how to do that and whether that serves you better. So the next thing, we made a fraction. So how does that work? We had defined this init, and then we had called fraction to make our fraction 1/2. And so clearly what happened was that init get called. Python doesn't make it quite that simple. It almost was for this class, but there's actually a pretty long chain of things that happen. So, for every problem, there's an answer that's clear, simple, and wrong. So first, making this instance was just calling fraction. So that call is defined by the metaclass. So if we didn't have a class, like earlier we had our Boolean enum, then calling it does something completely different than making an instance, and completely different from our init, and all of that. But in our case, it was a normal class. So what happens first is that under new gets called. So the difference between init and new does not take an instance. It takes the arguments that you've been called with and return either an instance or really anything else. Under new lets you use a class really as a function. It gets called with arguments, and those arguments could become anything. You can do whatever you want. You could return something completely different. One of the funny things about under new, though, is that if you return an instance of the class, then under init gets called. So depending on what you return, under init may or may not be called. Init, unlike new, receives an instance because there is an instance at that point. One common mistake I've seen when people use under new, I've actually seen in the wild people calling under init themselves. That can lead to under init being called twice, which can be pretty bad sometimes. So you can't forget metaclasses even after you've defined the class, because by the time you're making an instance or using it, you need to know, was this a class, was it not? Under new can be confusing to use, in part because someone calling your class expects an instance back, might not get it, and because you have to think through, depending on what I do, this other method may be called, it might not be called. Usually it's nicer just to use a function in that case, instead of giving your class an under new. But in any event, there's sort of this chain of things happening every time you make an instance of a class. So let's move to the next thing that seems simple, looking up attributes of our class and really dealing with attributes in general. It looks very straightforward. You can do it without thinking. It works really well without thinking. There's actually several layers here that affect what's going to happen. So for a normal lookup of a normal name, like numerator, print fraction, no special syntax involved, no brackets, no asterisk. What happens is that the instances get attribute method is called, and it walks through the instances dictionary. If it doesn't have a dictionary, the instances attributes itself, and then each classes. If it finds a method on, if it finds an attribute on the instance itself, it just gives it to you back. But adding complication, if it finds it anywhere else, and the thing that it has found is a descriptor, and we'll talk about those momentarily, the descriptor protocol is invoked. If it doesn't find any of that, under getattr is called. So under getattr is pretty familiar. It's called, when there's sort of a miss, when you look up an attribute, it wasn't otherwise found. Under getAttribute is a much more powerful beast, a much more low-level thing. Whenever Python is looking up a double underscore method itself, like under mul when we had an asterisk, it's going to skip the instance altogether. So you can't just put those on an instance. It's going to look them up on the class. It's going to know a bit about what to do with them. And so there's a difference there based on how you looked it up that isn't entirely equivalent. So we said that if the attribute's an attribute of a class, when it gets looked up, the descriptor protocol is involved. Descriptors let something special happen when an attribute is looked up or deleted or set or what have you at the attribute level. So there's these pretty easy to understand functions like getattr, setattr at the class level, but this is actually at the attribute level that has been assigned. This is the magic that lets methods work in these cases and a lot of other Python features. So the most common descriptors that people deal with are functions. Descriptors are what allow functions to become methods. Functions know how to bind themselves to objects, and we'll discuss that in a little more detail. But the same magic makes properties work if you've used the property built-in, class methods, static methods, things that in most languages would just be bare language features, could all be written from scratch in Python code in Python. If you wanted to make property and somehow you had lost the one in the main namespace, you could just make that. It's not a core language feature. Descriptors are what are the true core language feature. So let's say that we have an instance and we're looking up an attribute that was a method that we defined in the class. So like we said, we defined it as a completely normal function. So when we look in the class dict, that's what's there. It knows nothing about self. It knows nothing about the class. It's just a function like any other function defined anywhere else. What Python will then do, if it finds that on the class, not on the instance, is invoke the descriptor protocol. So in this case, since we're looking it up, we'd call under get if it exists. Under get is how a function turns itself into a method. So it'll be called with the instance itself and with the class, and it'll take that instance and make that self because it knows what it's been called on, and then return something that only needs to be called with the remaining arguments, not with self. This repeats C, and so just to be clear, you have a base class perhaps where the attribute's defined, but you actually get the type of the current instance passed in. That's really for historical reasons. It doesn't actually help you because you have the instance, but that's how lookup works when descriptors are involved. There's an under set and an under delete. Under del was already taken. That would be called if I had instance.attr equals or del instance.attr. And so, again, this only happens at a class, not on the instance itself. So if any of us were trying to monkey patch an instance somewhere, and we just set myInstance.method to some function that we had, that function won't receive self because that will be an attribute just of the instance, so descriptors aren't involved. So there's two main gotchas. This first one's sort of the bigger one when dealing with descriptors. Classes don't automatically work as descriptors when you give them under call. So if you think you've defined something that works like a function, you've given it an under call, that won't work as a method. It won't know to automatically receive self. So the main time that this is tempting, say you've defined a decorator as a class, that's a thing that makes a lot of sense to do. If you've not defined decorators, you might not understand why, but that's something that's very natural to do when defining a decorator. Then you'd think, oh, well, I call it, it'll be past self. That won't automatically happen. You'd have to write a descriptor yourself. That's sort of the main reason that someone might write a descriptor, and it's one of the reasons why a lot more people use closures, functions that return functions instead of classes for descriptors. Another gotcha is that if you're in Python 2 and you didn't inherit object, if you're using old style classes, classic classes, they don't really work completely as descriptors, but hopefully no one's making any new classic classes today. So we have to remember there's this whole onion whenever we look up or do anything else with an attribute. We'd go through get attribute, we'd go through all the dicts, some of them invoking descriptors, some of them not. Finally, get attr. So there's several levels here at which the implementer of the class that we're using or of our base class could have thrown and sometimes do throw monkey wrenches into the business. Set-attr and del-attr are not quite as complicated at the default, but work basically the same. And so decorators allow lookup to have a lot of magic. It's a very general mechanism that allows methods and many other things. They can be kind of hard to grope, but very powerful. Under get attribute is changing so much default behavior that it's almost always not going to be nice to use. It has several gotchas to it, and it would make you depart really far from what people are used to attribute access meaning. There's one other thing to attribute access and lookup that deserves note. That has an epically bad traceback if you want to debug it and figure out what's going on, and that's under slots. So Python allows you to define all of the attributes that an instance can have. This allows an instance not to have its own dict. It saves memory. So under slots, you set to a list of those attributes. So since we end up setting for the instance, numerator and denominator, so that's just on the instance, class attributes like methods aren't affected. And then we could use it, and it would look exactly the same. We could call that init. We could then go through our other methods. But if we tried to assign a new attribute that isn't in this list, so if I tried to set half.real to numerator over denominator, that's going to fail with fraction object has no attribute real. So if you end up getting handed something with slots and for some reason, hopefully for debugging reasons, try to set an attribute on it, then it can fail in this way. It doesn't give you much indication of what actually happened, but that's sort of the one final asterisk I wanted to present regarding attributes. So under slots, again, if you're going to have a lot of instances, it's something that saves memory. The way I tend to see it, by the time you're at that level, you probably want to define a C extension or use a C extension or something, that's sort of this in-between optimization that hasn't turned out to be useful, at least for user code, I don't think, all that often. And, our little instance, had a good life. It was half. It halved itself and became quarter. But eventually, it's going to fall out of scope and get garbage collected by Python. The method under del is called when Python garbage collects an object, maybe. Python actually doesn't promise to call del under any circumstances. It is not as apt to be called if you had a reference cycle in CPython, because it doesn't know when to call them. It's less apt to be called if your objects survive and the interpreter is coming to a stop. If del itself increases the reference count of your object somehow, it's actually might be called again and again. Who knows? It's a pretty tricky beast. If something goes wrong in Del, well, it wasn't called in your code, so there's no traceback, so it just barfs to standard out because that's really its only option at that point. And so it's really not that reliable. In languages like C++ or Rust, people use the RAII paradigm, and the destructor is a very important thing for managing your resources, for making your code sensible. And a lot of people might look at under Del and think it's good for the same thing, but it's not, because it's not reliable, it's not predictable, it's not tied to scopes the way that you can have things tied in a language like C++. And so it's much more squirrely. A lot of people would go so far as to say it's not a destructor because your object might not be destructed, and certainly it's not doing that work. So best practices for using under Del: don't use under Del. Or if you are, let it be a backup. If you really have to send the end session, close the file descriptor, whatever, try to have it happen another way, but if you really insist, maybe under Del is a place you can put that. So Python's built-in file type, you open it with open. Ideally, you'd close it yourself with the with statement or with the close method. But if it's garbage collected under Del, it will close that, or really, to C level, the equivalent. Python does provide good ways to make sure things actually happen. The first is context managers, the with statement. And so that will ensure that something happens. In this case, a file actually gets closed. And it provides try finally, this way to make sure something happens. Del, unlike destructors in a language like C++, is not a good way to make something happen when you're done with an object. So we've seen that if we look in detail at Python, things that look really simple, really basic, nearly hello world, are actually really complex. We started with this 7-line fraction class, and it turns out that we had metaclasses and descriptors triggering and these really obscure things that, when tweaked, can be really hard to find because they're so invisible. So these hooks are there for almost everywhere. If there's been any bitterness in my voice at certain points in this, it's because I've had to debug code that was using some of these. Sometimes it can be really subtle, and so I hope that I've conveyed to you where to look. If everything seems to add up, but then something is happening you can't understand. Maybe it was within a meta class you didn't know you were propagating, or what have you. These things can also be incredibly useful for machete debugging. If any of you made it to Ned Batchelder's talk earlier today, a lot of these hooks are great for what he termed machete debugging, where you want something to happen right in the middle of everything when it seemed like there's no way to insert your code. And so this temporary code you want to debug with can actually be really beneficial to allow tracing and code to insert itself. That you aren't going to leave around, you aren't going to have to debug, you aren't going to have to understand really subtle things to make it work. So that's what I have for you today. I hope that I managed to convey pretty well sort of when these things happen and how you might be able to see them and debug them if they ever come up in code you've written.
So we have time for questions. If you have a question about the speaker's talk, please step to the microphone here. Has the situation for cyclic references changed in later Pythons, or?
So the question is, the situation for cyclic references changed in later Pythons. Mm-hmm. So with reference to under Del,
Or just the success of the garbage collector, yeah.
CPython still uses, reference counting as its primary technique, and then a cyclic garbage collector that's kicked off. There's been slight optimizations, I know. I don't know anything deep about them, but it doesn't have a more sophisticated garbage collector. Other implementations, Jython uses whatever JVM's more powerful garbage collector. PyPy has a somewhat pluggable family of really sophisticated garbage collectors, but CPython still primarily reference counting.
Can you give an example, if you've ever seen one, of a valid use for under-underdel?
So the question's an example of a valid use for under-underdel. From my point of view, I think the only time that makes sense is when you want to make something happen when something's gone wrong with the use of it. So I think files under-underdel, or it's actually the C-level equivalent, makes a lot of sense. It will close that descriptor for you. But that's not how it wants you to do that. It wants you to call close, either directly or with the with statement. So if you're writing something that needs something to happen, you might make it a context manager or give it an end method or whatever, and politely ask that to get called. But for safety, yeah, maybe you do call your under-underdel just in case something's gone wrong. That would be what I see as valid use of under-underdel.
Thank you.